Welcome to another video for Stat 212. In this video, we're going to be looking more at the properties of sampling distributions for the sample mean. So again, this is kind of the statistic that we're going to focus on the most as just being kind of an important statistic that we're often going to use in inference later on. So we're going to kind of look at an example here and think about how the sampling distribution for a sample mean is going to behave in some different circumstances. So I'm going to be using this sim that is at the link posted there in the notes, and I'd really encourage you to open that and use that during this video. So we're going to kind of have a prompt here, we're going to set it up, and then I'll kind of let you know at what points you might want to pause and complete a task or two before continuing. So here we have kind of an open question. What is the earliest age at which an American takes their first ride on an airplane? So if you think about different people in the country and you ask them this question, have you ever flown on an airplane? And then secondly, what was the earliest age at which you did that? What would be the distribution of ages that we saw? So, assuming we're looking at those who said yes to this question, who have flown on an airplane, what is the distribution of ages that we're going to see as responses? What are the youngest ages that we're going to see? What are the older ages that we'll see? What are the most common ages that we'll see? So I would encourage you to pause the video and to kind of sketch out what you think this distribution might look like. You don't have to know what it looks like, because I don't know what it looks like either. It's more just to kind of get us brainstorming here for this particular activity. And I think it's kind of fun to work with something that we don't necessarily know, because we can try different distributions to see what would happen. So I kind of label it from 0 to whatever age you think might be the maximum that you'd commonly see, and then just kind of fill in how high or low that distribution is for different ages. So I'm going to fill in mine. I'm going to just go ahead and cap this one at 32, not because people don't take their first airplane ride afterwards, but because we're going to be using a sim that naturally maxes out at 32. So I'll just be kind of consistent with what I'm going to do on the sim here. I think that there's a few who've taken a ride on an airplane when they were infants, like 0, 1, 2. So I'll kind of do a little bit of a line here, but I think the number is going to be much more likely kind of around these younger kid ages. And then I imagine this kind of slopes off a little bit as we get to higher and higher ages, that there's fewer and fewer people left taking their first ride at higher ages. So I might kind of put this cap around 10, somewhere around 10. And then we're going to have kind of 20. This doesn't quite come out right. I guess my 32 is going to be off a little bit, so maybe I'll revise a little bit. Maybe I can kind of back up a little bit too. So there's my 32. So this is what I think it might look like. However, again, this is just a guess, and you might have drawn something different, and that's totally okay. Okay. Now the second question here is to sketch your population on the left, but I also want you to think about what would happen if we were to ask 10 random people from this population what was the first age that you rode on an airplane, and then we take the sample mean from that sample of 10. So we basically report the average age of first ride on an airplane for this group of 10 people. What are the different sample means that I'm most likely to see? Like, what's the smallest sample mean you expect to see? What's the largest sample mean you expect to see? And what sample mean do you think you're going to see the most of? So what we're going to do now, so we created our population that we think represents the population. Now, so we sketched our population on the left. Now we're going to sketch what we think the distribution is going to look like on the right. So I'd encourage you to kind of think about that on the right first, and then I want you to open the sim up with me. So actually, let me think about this. I'm not doing this in class. It's a little bit weird because I actually have to open this up too. How about this? Pause on the question. We're just going to discover it together on the sim. So what I'm going to do is I'm going to pull up the sim right here, and I'm going to kind of reshape this a little bit. So if I just click here, and you can do the same, you can reshape this population to look the way that you drew your distribution. So mine look kind of like this, and I'll kind of make that a little bit progressive there. So this is what mine look like. If yours look different, you can draw it a little bit differently. And so what I'm going to do is I'm going to animate taking a sample of 10 by clicking here. And then I'm going to animate this. I'm going to click the animate button. This is like drawing a random sample of 10 people. And this is the sample mean that I got when I drew this sample of 10 people. And I'm going to do this again. I'm going to draw another sample of 10 people from this population and draw another sample mean here. So this one's about maybe like 8 or 9. This one's about maybe 15, 16. So this one's a little bit older, and I could do this again. Get another sample of 10. Right, so this is going to get really tedious really quickly if you can't tell, right? So that's why there's some shortcuts over here. So if I don't want to keep doing it one at a time, I could just quickly sample 5 people and 5 sample means and do that. Or I could even do 10,000. And if I do 10,000, I'm going to get a distribution of possible sample means that begins to look a little bit more symmetric around the true population mean. So here is this one's the true population mean, the blue one. My sample mean is lining up pretty close to that here. My sample mean is this red bar. The population mean is this blue bar. And so I can continue doing that and kind of ensure that I have the true kind of shape here. So here I'm going to go back to the notes now, and I'm going to draw this distribution of possible sample means here on the right. So starting around 0, ending around 32, my distribution of possible sample means started around, let's see, 1, 2, 3, 4, about 7 or 8, and then kind of went up like this. I'm probably not giving, you know what, I need to make a little bit more room here because I am drawing too big. Here's 32. So here's about 8. Apparently my population means around 12, so I'm going to put 12 about here, about 16. So really what's going on is I have a distribution that looks kind of like this. Skews out a little bit to the right. My distribution of possible sample means is going to be centered around kind of that 12 value, which is the population mean apparently for the population that I drew. And this is a good place for you to kind of pause and think about your own. So if you drew a different distribution, you got a result, and you should think about each of these questions. From your collection of averages for samples of size 10, what was the smallest and largest sample means that you got? So in my case, I believe that my smallest sample mean, if I pull it up here, is 1, 2, 3, 4, 5, 6, maybe 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I got about from 7 to 20, maybe 7 to 19. So let me come back here. So you should do that the same thing for your own there. I'll just say 7 to 19. That's about right. And now at this point, now we're going to use the sim again, and this time we're going to think about what happens if I take larger samples at a time. So what if I take 25 people at a time and ask them their average age on an airplane, right? So I'm going to have my sample mean of 10 up here. That's 10 people. But then if I ask 25 people, I'm going to get a lot more data. And so maybe my sample mean is going to be a little bit more accurate in estimating the true population mean. But if I'm only taking one sample of each, it's kind of hard to compare. So that's why I need to look at this distribution of possible sample means. So we're going to do some probability here, where we're starting from the truth. We're starting from this assumed distribution, and we're thinking about what could happen if I take samples. What sample statistics am I going to get, and how likely am I to get them under this assumed truth? So if I take 10,000 samples for each very quickly, you'll see that my distribution of possible sample means for samples of size 25 is a lot more accurate and it's a lot more narrow, right? Because I'm getting much more trustworthy sample means in this context. So if I kind of go back over here to my notes, what was the smallest and largest sample means that I got over here? It looks like I'm around, let's see, 11, 10, 9, 10, 11, 12, 13, 14, 15, 16, maybe 9 to 17, 9 to 16, something like that. Let's see, 13. I think it's 9 to 17. Also describe the shape of your population distribution when n equals 10 and the sampling distribution when n equals 25. How are they different? So this is a really good question. They're both pretty similar in shape, right? It's just that one is going to be a lot narrower than the other. I say a lot, I mean noticeably narrower than the other. And they're also both becoming a little bit more symmetric around the true population mean, right? So maybe this one isn't quite like, this one still has some skew. This one's a little bit more symmetric, I think. So I'll kind of make that note, make that note here. The n equals 25 example is more narrow and slightly, lost. I don't know what I'm writing anymore. I'm butchering this word. Okay, slightly more symmetric. But they're both similar in the sense that they're both kind of relatively symmetric, and they're both centered around the true population mean. Okay? And so now let's pull things together. If you continue to increase the sample size, what do you think will happen to the distribution of possible sample means? So this is a good question for you to, again, pause and think about. If we continued increasing the sample size, what do you think would happen to this distribution of possible sample means that I'm creating? And hopefully, you're kind of pulling together here that the larger the samples I take, the more accurate the sample means tend to be, and thus the narrower the distribution of possible sample means is going to continue to get, right? So the larger n is, the more accurate and narrow we could also kind of use the word clustered, right? So the sample means are clustering more and more around that true parameter, right? They're, it's almost like they're attracted to the parameter, and the larger the sample size gets, the more that attraction becomes obvious, that they're just like really hugging that population mean. So that's kind of an important consideration to have here. Okay. Now, I've already used this word before, and I honestly shouldn't have used it on the previous page until we got here, is I want to talk about this term sampling distribution because it's a little bit confusing because we have two words here that are super similar. And I'm not responsible for this, by the way. You can thank the development of the discipline that we have these two awfully confusing words. However, they exist, and so we need to use them. So the first one is a sample distribution, and that is describing the shape of the sample results that I get. It's the individual observations that I get in my sample, right? So if I'm rolling dice, I'm representing the individual dice rolls that I have from 1 to 6. So I have some 1s, I have some 2s, I have some 3s. Now a sampling distribution is describing the distribution of possible sample statistics that I could see when I take samples from this population. So sample distributions are going to kind of converge around the population shape, the population distribution shape. Sampling distributions are going to converge around a singular point if I take large samples. So the larger sample I take, the more the distribution of possible sample statistics should be converging to whatever parameter it's trying to estimate. Okay, so these are two different terms that you should be really careful with and distinguishing when we're talking about each one. So as we mentioned before, we can create a sampling distribution for any sample statistic for any sample size. And as n increases, the sampling distribution is going to converge to the parameter it's estimating. If it's an unbiased estimator, then it will converge symmetrically. If it's a biased estimator, then it will converge more asymmetrically towards that parameter. Okay. So let's focus a little bit more on the distribution of sample mean. So the formal name here, we call it the sampling distribution for the sample mean. It represents all the possible sample means that I could get for a particular sample size, for a particular distribution variable that I'm working with. So one thing that you might have noticed already is that not only is the distribution of possible sample means kind of getting narrower and centering around the true mean, it's also taking this kind of normal distribution shape. So we talked about normal distributions earlier. It's when we kind of have this bell shape around a particular value. So sample means do that. Sample means distribute normally if I have a large enough sample size that I'm drawing from here. So that's kind of a cool thing, right? So normal distributions appear a lot when we're working with certain variables, and they obviously appear now. We're talking about how a sample statistic may distribute around its parameter. And so we can kind of use that to our advantage when we get to inference a little bit later. So in the next chapter, we'll talk more about, so we have our one sample, what do we do with it? What can we say about a population if we only have one sample? And so it kind of starts from this discussion of, well, if I know what's really going on, if I know that my sample statistic exists within some distribution of possible sample statistics, and I know that that distribution is shaped normally, and I can maybe figure out about how wide that distribution is, given some information, then I can estimate about how close I should be to that parameter. So we're going to get to that a little bit later on. But for now, the big idea here is that our sample statistic, like the sample mean, exists within a distribution of possible sample means that we could get. And that distribution is going to tend to be normally distributed around the true population mean. So you can kind of test this if you want. If you wanted to open up the sim, for example, you could make kind of the funkiest distribution that you can think of, right? So if I made something that looks kind of like, crazy, it doesn't really matter what the shape is going to be. If I'm taking, let me make this none. But if I take sample means, they're going to tend to distribute normally around whatever that true mean is. Now, the only case where that doesn't happen as clearly is if my population is really, really skewed. So if I do something like this, it may not emerge as obviously, right? Well, this one actually it does pretty well. So let me make it a little bit more crazy. So here's a really skewed distribution. So if I take sample means from this one, you're going to notice a little bit more skew now, right? So it's a little bit right skewed. But if I take a larger sample size for each one, so if I'm taking sample sizes of 25 and taking those means, that's going to be a little bit closer to normally distributed. It's going to be a little bit more symmetric. So that's one thing that we kind of want to carve out here is properties of sampling distributions. So the first one is that the mean of a distribution of means should be equal to the population mean. In other words, the sample mean should be an unbiased estimator of mu. The sample mean should be clustering and centering around whatever the true parameter is. So that's what we mean by that first property. Secondly, which we're going to talk about more in the next section, the standard deviation of a sampling distribution, which we often call the standard error, is going to be equal to the population standard deviation divided by the square root of the sample size. this might seem a little bit odd and might be a little bit out of place compared to where we are so far in our kind of development of this. But this is something that we're going to talk about again a little bit in the next section, is that we can kind of quantify how wide and how variable a distribution of possible sample means is. We could do it for any sample statistic, but we're going to focus on how much variability we see in sample means. And third is what we were kind of pointing out there at the end, and that is that sample means tend to distribute normally, whether the distribution is already normal or even if the distribution is not already normal that we're sampling from. So if the distribution that we're sampling from is already normally distributed, then this is just universally true. It's true from the very beginning. If the distribution that we're sampling from is not already normally distributed, then this distribution is going to be approximately normal if n is large enough. So we have to say that n is large enough part because if we have a really skewed distribution, then right like the n equals 10 didn't quite work. The n equals 25 even wasn't perfectly normal either. So if the distribution is more skewed, then we need a larger sample size to know that the central limit theorem, to know that this normality thing is going to be true for our sample means. So we call this the central limit theorem. That's what we call this property, is that regardless of what shape we see, this phenomenon is going to happen if n is large enough. That for any distribution shape that I could have, there exists an n that I can get to where the sample means that I kind of generate are going to be normally distributed around whatever that true parameter is. So this is really important because when I'm doing inference later, I may not know the exact shape of the population that I'm sampling from, which is partly why I'm doing inference, is because I don't know. But I can take a sample and I know that the distribution of possible sample means that I'm gathering my sample statistic from is probably going to be pretty normally distributed, assuming that I have a large enough sample size. So that's why this is kind of important, is it's really key for doing inference later on.